Imagine waking up one night, stepping outside, and realizing that every light in the sky is a window. Behind each window could be oceans, forests, cities, languages, and histories as rich and messy as our own. For most of human history, we assume those windows were empty, or at best, home to distant gods and myths. Then modern astronomy arrived and quietly destroyed that comfort. We now know our galaxy alone holds hundreds of billions of stars, and probably even more planets. Many of those worlds sit in the gentle band where liquid water could exist. Statistically, it feels almost impossible that we are the only ones. Yet when we listen, we hear nothing. When we look, we see only stars. So the question that keeps scientists awake is simple and unnerving. If the universe is so fertile, why does it feel so alone? This puzzle has a name. It is often called the Fermi Paradox, after a lunchtime conversation in the 1950s, when physicist Enrico Fermi supposedly looked up from his meal and asked, "Where is everybody?" Imagine sitting at that table with him. By then, humanity had just begun to understand nuclear power and rocketry. The galaxy was no longer a poetic backdrop. It was a place, with distances you could write down and crossing times you could calculate with a pencil. Fermi realized that if even one civilization started exploring and colonizing space, using technologies only a little beyond ours, it could spread across the Milky Way in a tiny fraction of the galaxy's lifetime. Not in a science fiction instant, but fast enough that we should see the fingerprints by now. Yet we do not. That contradiction sits at the heart of our story. To feel how strong this contradiction is, we need to put numbers and timelines on it. The Milky Way is more than 10 billion years old. Earth formed about 4.5 billion years ago. Life appeared on our planet surprisingly quickly once things cooled down enough for stable oceans. For billions of years, it stayed microscopic, then exploded into complex forms, eventually giving rise to beings like you and me. From the moment our ancestors began using tools to the moment we started sending radio signals into space, took only a tiny sliver of planetary time. If even a small fraction of worlds follow a vaguely similar arc, the night sky should be alive with cultures at all stages of development. Astronomers sometimes step back and ask a forward-looking version of the same question. Imagine our own species, or whatever might evolve from us, managing to avoid self-destruction. We learn how to build vast solar power stations in orbit. We build faster, more efficient engines. We send probes to nearby stars, then heavier ships, then swarms of self-replicating machines that can mine asteroids, build copies of themselves, and keep moving. None of this requires magic. It only requires technologies that sit a few steps beyond what we already understand on paper. On timescales of many millions of years, those swarms would not just visit a few nearby stars, they would wash across the whole galaxy. If someone else had done this long ago, the evidence should be everywhere. This line of thinking was sharpened by researchers like Michael Hart and Frank Tipler. They argued that you do not even need biological beings to cross the galaxy. You just need machines that can build more of themselves from local raw material. A single seed probe, launched by an early spacefaring civilization, could arrive in a new star system, harvest metal and rock, and construct a small fleet of children. Those children would spread to more systems and repeat the process. Even with modest speeds, the wavefront of exploration would spread through the Milky Way in what is, cosmically speaking, the blink of an eye. Their conclusion was harsh. If such expansion is so easy and so fast on galactic timescales, and if nobody has reached us, then maybe nobody is out there at all. At first glance, that seems like a clean solution. The universe is quiet because we are the only technological species that ever arose, or at least the only one in our galaxy. But as data piled up, this answer started to look less convincing. When the Fermi Paradox was first discussed, we did not yet know whether planets around other stars were common. They were an informed guess. Today, we have catalogs of thousands of confirmed exoplanets. We detect them through tiny dips in starlight when planets transit in front of their stars. and through the subtle gravitational wobbles they produce. These discoveries suggest that planets are not rare prizes. They are the default outcome of star formation. Even more importantly, we now see planets in or near what is called the habitable zone around their stars. This is the range of distances where temperatures on a rocky world could allow liquid water on the surface. It is not a guarantee of life, but it is a promising starting point. Red dwarf stars, which are smaller and longer-lived than stars like the Sun, have planets that sit in these temperate bands and may stay there for trillions of years. When you add all this up, the number of potential homes for life just in our galaxy becomes mind-bending. Multiply that by the number of galaxies in the observable universe, and the idea that we are the only ones starts to feel less like sober science and more like an extraordinary claim. Scientists often organize these factors into something called the Drake equation. It is not a single number to be solved like a school assignment. It is more like a checklist of questions. How many stars form each year in the galaxy? What fraction of those stars have planets? On how many of those planets does life begin? On how many does life become intelligent? How many intelligent species build technology that can be detected across interstellar distances? How long does a typical technological civilization last before it collapses or transforms into something unrecognizable? Each term is fuzzy, but the equation forces us to show our assumptions. With modern exoplanet data, the early terms in this chain look generous rather than stingy. Here is where the tension really bites. When astronomers plug in numbers that are at least plausible and not absurdly pessimistic, they often find that our galaxy ought to host many communicating civilizations, perhaps thousands, maybe more. These would not all be contacting us at once. Many would be too far away, or on different timelines, or transmitting in ways we cannot yet see. But some should overlap with our brief window of listening. Some should be broadcasting bright beacons or lighting up entire star systems with energy use that leaves signatures in the infrared. If the universe were that busy, we would expect at least a few obvious, unambiguous signs by now. Instead, we have silence. It is important to be clear about what we mean by silence. Humans have been conducting dedicated searches for extraterrestrial signals for only a few decades. Our radio telescopes have scanned only thin slices of the sky in limited frequency bands for relatively short periods of time. The part of the galaxy we have carefully listened to so far is like a tiny puddle on the shore of a cosmic ocean. So we should not be surprised that we have not yet heard a clear hello. At the same time, there are kinds of activity that would be very hard to miss. If a civilization built enormous structures to harvest most of the light from its star, or if a wave of industrialization swept across many neighboring systems, we might see clusters of stars with strange, dimmed spectra and excess waste heat. Large-scale astroengineering projects are the kind of thing that radiate their existence, whether anyone is trying to stay hidden or not. So far, surveys of the sky have not revealed huge populations of stars that look obviously altered by advanced engineering. There are curious objects here and there. A few stars have shown odd dimming patterns that spark speculation. Some galaxies show puzzling features in their light, but none of this yet rises to the level where the scientific community agrees we are looking at the handiwork of someone else. Every time a candidate technosignature appears, astronomers patiently search for natural explanations. Nearly always they find one. Dust clouds, instrument glitches, stars that behave in ways we did not fully understand. The pattern is humbling. The universe remains stubbornly natural. You might wonder whether we are simply not looking in the right way. Perhaps advanced civilizations do not shout with radio beacons. Maybe their technology is subtle, efficient, and designed to blend in with the background. Maybe they communicate using narrow laser beams, neutrinos, or physics we have not discovered yet. These are reasonable possibilities. Still, there is a deeper version of the Fermi Paradox that does not care about how the signals are sent. It cares about occupancy. If spacefaring cultures are common and expansionist, then the volume of the galaxy should be dominated by regions that those cultures have already reached and reshaped. If we are sitting in the middle of one of those regions, it is strange that we do not notice. If we are not, then it is strange that nobody has reached this region yet. A helpful way to feel this is to imagine the Milky Way as a vast forest. Each technological civilization is a fire that can spread from tree to tree. Once a fire starts, it may flicker out, sputtering and dying in a few nearby systems. But even if only some fires manage to grow, and even if they start at different times, over billions of years, you would expect most of the forest to have burned at least once. That does not mean everything is destroyed. It means the forest would bear the marks of those past events. Charred trunks, clearings, new kinds of growth in the burn zones. Right now, when we look out with our best instruments, we do not see obvious burn scars in the galaxy. We see a forest that looks, at large scales, untouched. Another subtle piece of the puzzle comes from thinking about when Earth appears in cosmic history. Our planet formed after many other generations of stars had already lived and died. Heavy elements like carbon, oxygen, silicon, and iron are forged in the hearts of stars and in the violent deaths of supernovae. The first planets in the universe would have been made mostly of hydrogen and helium, with very little of this rocky material. As time went on, each wave of star formation enriched the galaxy. That means there was a long stretch of cosmic time before Earth formed, when other rocky, potentially habitable planets could already have existed. If intelligence and technology can arise on such worlds, some civilizations could easily be billions of years older than us. This pushes us toward a disturbing realization. If older civilizations had even a slight appetite for expansion, they have had far more time than they needed to reach us. Even very slow strategies, like sending out probes that crawl at a tiny fraction of the speed of light, would, over hundreds of millions of years, fill much of the galaxy. If nobody has arrived here, perhaps nobody ever chose to expand. Or perhaps those that did expand were wiped out by dangers we do not yet understand. Or perhaps the very fact that we are still uncontacted is telling us something statistical about where humanity sits in the grand timeline of life. Each possibility leads to a different kind of fear. So where does this leave us? On one side, we have a universe that looks, from the outside, incredibly friendly to the rise of life. We have countless stars, abundant planets, long-lived stable systems, and a cosmic history that has been producing heavy elements for billions of years. On the other side, we have the Hart and Tipler-style argument that says expansion is easy, so if somebody could have spread by now, they should have, and we would see the evidence. Between these two pictures lies a sharp contradiction. Something in our understanding is wrong. Either life is much rarer than we think, or expansion is much harder than it appears, or those who expand do so in ways that are invisible or short-lived. As we probe this contradiction more deeply, we are forced to ask uncomfortable questions about ourselves. Are we really typical? Just one more civilization drawn from a vast population spread across the galaxy? Or are we a freak outlier, lucky to exist at all? These are not just philosophical puzzles. Our assumptions about how common life is and about how long advanced cultures tend to last shape how we think about risk, responsibility, and the long-term future of our species. If most civilizations self-destruct soon after they unlock nuclear power and global networks, that suggests one kind of story we might be living through right now. If instead most civilizations survive and expand, then the silence around us points to some deeper mystery in how they choose to behave. We have built a case file filled with clues. The age of the galaxy, the ease with which planets seem to form, the speed at which a determined culture could, in principle, cross interstellar space, the stubborn absence of obvious astroengineering signatures. Each clue seems clear when viewed alone. Together they refuse to fit into any neat, reassuring picture. Somewhere in this mismatch between expectation and observation lies the real solution to the Fermi Paradox. To find it, we will have to explore ideas that challenge our sense of safety and our assumptions about what it means to be early, late, or completely alone in a vast and indifferent universe. When we talk about life in the universe, it is tempting to picture a gentle cosmic neighborhood full of blue skies and quiet sunsets stretched across 1,000 distant worlds. The real universe is nothing like that. It is a place where stars explode without warning, where entire atmospheres can be stripped away, and where a planet that looks safe for a few 100 million years can turn lethal almost overnight. If you zoom out in time, habitability is not a steady state. It is a moving target that planets are constantly chasing and often losing. Seen through that lens, the mystery is not why the universe seems so quiet. The mystery is how anything manages to stay alive long enough to start asking questions at all. Early Earth itself was not a tranquil cradle. For hundreds of millions of years after it formed, our planet was hammered by impacts from leftover debris in the young solar system. Some collisions were so violent that entire oceans would have boiled away, only to condense back later as things cooled. The crust was thin and unstable. Volcanoes belched toxic gases into a thick, murky atmosphere. The young sun was less steady and showered the planet with high-energy radiation. If you could stand on that world, you would not see a comfortable home. You would see a barely contained chaos, with narrow pockets where chemistry could survive between disasters. And yet, somewhere in that chaos, simple molecules began to copy themselves. The path from basic chemistry to the first self-replicating systems is still one of the deepest puzzles in science. We do not yet know whether this step is almost inevitable whenever conditions are right, or whether it required a chain of coincidences so improbable that it might have happened only once in the observable universe. This is the first hint of what some researchers call the Great Filter. Somewhere on the road from dead matter to galaxy-spanning technological cultures, there are stages that almost never succeed. These stages act like sieves, letting only a tiny fraction of possible worlds move forward. To understand how unforgiving those sieves might be, it helps to look at the universe as a whole. Planets form in disks of gas and dust around newborn stars. Some orbits end up too close, where any oceans would boil away and the atmosphere might be ripped off by stellar winds. Some orbits end up too far, where any water would be locked in ice and chemistry would grind almost to a halt. Even in the so-called habitable zone, the right distance for liquid water, a planet can still go wrong. A slightly thicker atmosphere and a bit more greenhouse trapping, and you get a runaway oven like Venus. A thinner atmosphere and weaker greenhouse effect, and you get a frozen desert like Mars. The sweet spot for long-term surface oceans is narrow. Staying in that spot for billions of years is even harder. On top of these local challenges, the galaxy itself throws tantrums. Massive stars live fast and die young, ending their lives in supernova explosions that flood nearby space with radiation and high-energy particles. Closer in, a planet in the wrong place at the wrong time can have its ozone layer shredded and its surface sterilized. Even more extreme are rare events called gamma-ray bursts, which unleash focused beams of destructive radiation across huge distances. If one of those beams swept across an otherwise promising world, it could wipe out complex ecosystems in minutes. Over the history of a galaxy, these events act like cosmic resets, erasing progress on many worlds before evolution gets very far. Despite all this, Earth did not just cling to life. It climbed, step by step, from simple cells to complex organisms. That story looks smooth when told in a few sentences, but it is anything but smooth in reality. For billions of years, life on Earth remained microscopic. Single-celled organisms ruled the planet, exploring almost every chemical niche, but never forming large bodies with bones, muscles, and brains. Then, in what looks like a cluster of transitions, more complex cells with internal compartments appeared. Cells began to cooperate, forming multicellular organisms. Nervous systems evolved and eventually supported perception, memory, and learning. Each of these transitions may have been highly improbable. Each could represent a filter that most worlds never pass. This is the core idea of the Great Filter. Picture a ladder made of many rungs, stretching from basic chemistry at the bottom to spacefaring civilizations at the top. A planet starts at the bottom and climbs, but most steps are slippery. At some rungs, the ladder is broken entirely. Maybe life starts easily, but almost always stalls at simple bacteria-like forms. Maybe complex cells are the sticking point. Maybe multicellular life is the real bottleneck. Maybe intelligence that can build telescopes and rockets is so unlikely that it appears only a few times in a galaxy. We do not know which rung is the hardest. We only know that if the Great Filter is real, somewhere along this ladder, most attempts fail. There is an even darker possibility. The true filter might not be in the deep past. It might sit in the future, waiting for species that have already mastered tools, agriculture, industry, and global communication. On this view, the universe could be full of intelligent life that routinely reaches our current level of technology. The reason we do not see thriving empires in the sky is not that they never start. It is that they almost never survive the leap to long-term stability. They unlock world-changing powers faster than they unlock the wisdom to use them safely. Nuclear weapons, engineered pathogens, climate disruption, uncontrolled artificial intelligence, and other hazards might be the real teeth in the filter. If that is true, then the silence of the galaxy carries a very specific warning. It suggests that the phase our species is entering right now is not a gentle slope toward maturity. It is a tight bottleneck that most civilizations do not squeeze through. Look at our own history. In just a few centuries, we have gone from burning wood and whale oil to rearranging the climate of an entire planet through fossil fuels. We built weapons that can destroy cities in a flash. We created global networks that can spread knowledge or spiral into misinformation and instability. None of this required changes in our biology. It required only our existing brains amplified by tools we barely understand. The risk is that our technological reach has outrun our emotional and political evolution. To feel how precarious this might be, imagine a distant world that looks, for a while, a lot like ours. Its inhabitants discover electricity, radio, internal combustion engines. They build cities that glow from orbit. They map their genome and begin to tweak it. They deploy machine learning systems that can shape public opinion. They send their first probes into orbit and dream about reaching nearby moons and planets. From a telescope on Earth, that world would shine with techno-signatures, brief pulses of communication, and perhaps the excess infrared glow of waste heat from heavy industry. Then, over a short geological moment, those signs would fade. Maybe there was a war. Maybe their climate crossed a tipping point. Maybe their own machines slipped from their control. The point is that the light went out. Multiply that story by millions of planets. Each gets its own timeline, its own mixture of successes and failures. Most never get past simple life. A few climb to intelligent, tool-using creatures. A tiny handful reach early industrial technology. Of those, only a fraction manage to build a stable, sustainable civilization that can last for millions of years and spread safely beyond their homeworld. If that fraction is small enough, then even in a galaxy full of life, the number of long-lived, spacefaring cultures alive at the same time could be close to zero. When you look up at the stars, you might be seeing the resting places of thousands of failed experiments. Of course, this entire picture is built on one sample. We only have Earth. We do not yet have a second example of life, whether microbial fossils on Mars, strange chemistry in the clouds of a gas giant, or clear biosignatures in the atmosphere of a distant exoplanet. Without a second data point, we are guessing about how steep the filters are. That uncertainty cuts both ways. If we discover that life appears easily wherever conditions are decent, then the early rungs of the ladder are not the problem. The filter, if it exists, must sit later. That would make our current century feel even more dangerous. If, on the other hand, we discover that even simple life is extremely rare, then perhaps we have already passed the hardest hurdles and do not yet realize how special that makes us. There is another twist. The universe itself changes over time. Early on, galaxies were more chaotic. Star formation was more violent. Heavy elements were less abundant. Radiation was harsher. As the cosmos aged, conditions became more gentle in some ways. Long-lived stars like red dwarfs formed in huge numbers and settled into slow, steady burning. That means there might be a preferred era for life and intelligence. Some researchers have suggested that complex technological civilizations might be more likely to appear trillions of years from now, orbiting quiet red stars, than in the present age. If that is true, then we are early by cosmic standards. Being early can be good news because it suggests the great filter may mostly lie behind us. But being early also creates a different kind of tension. If we really are among the first technological civilizations in the galaxy, or even in the observable universe, then we carry a responsibility that is hard to wrap your mind around. Our survival or failure would not just matter to our descendants, it would matter to whether the universe gets to explore certain possibilities at all. Maybe most galaxies never get a chance to turn matter into minds, minds into cultures, cultures into explorations that reach across interstellar space. If we are one of the first who could do that, then falling to our own mistakes would mean slamming a door that might otherwise have stayed open for billions of years. You can feel the soft pressure of this idea whenever you hear about existential risks on the news. A nuclear standoff, a new bioengineered virus, a report on accelerating ice melt and shifting climate patterns. These are not just local dramas. In the Great Filter framework, they are potential bottlenecks in a process that might be incredibly rare. When you think about it this way, the usual question, what if we are not alone, flips itself around. We start to ask, what if we are alone for now? Because almost nobody makes it through this phase. If that is the case, then the quiet of the sky is less like an empty room and more like the pause after a long series of accidents. Yet the Great Filter does not have to be a purely pessimistic story. It can also be seen as a challenge. If there are filters in the future, they are not abstract cosmic forces. They are made of our own choices and technologies. We have some control over how dangerous artificial intelligence becomes. We have some control over whether we pour greenhouse gases into the air or build cleaner energy systems. We have some control over whether weapons of mass destruction are kept on hair-trigger alert or slowly dismantled. None of this is easy, but thinking in terms of filters turns vague worries into specific coordination problems. It tells us where to focus if we want our species to be one of the rare ones that makes it through. At the same time, we cannot ignore the possibility that some filters are truly external. A nearby gamma-ray burst is not something a young civilization can prevent. A wandering black hole passing through a system, or a slow drift of orbits that destabilizes climates, would be almost impossible to foresee in time. These risks remind us that the universe does not owe us a future. We live in a narrow band of safety carved out between countless forms of disaster. Recognizing that might feel frightening at first. It can also be energizing. If the cosmos is that indifferent, then any flourishing that does happen is even more precious. As we weigh these possibilities, it becomes clear that the Great Filter is not just a theoretical idea scribbled on a whiteboard. It is a way of framing the story of life in the universe as a sequence of gambles. Each world rolls its own dice. Each step toward complexity, intelligence, and technological power is a bet that the gains will outpace the new vulnerabilities. Right now, our species is in the middle of one of the most dangerous bets of all. We are learning to reshape not just local environments, but the entire planet, and soon, perhaps, parts of the solar system. The question hanging over us is whether we can learn faster than we break things. If the galaxy is mostly empty because the filter is behind us, then we may already be one of the luckiest civilizations that will ever exist. If it is empty because the filter lies ahead, then we are living on borrowed time, inside a statistical fluke that will not last unless we deliberately change our trajectory. Either way, the silence of the stars forces us to treat our moment as something other than business as usual. It is a diagnostic hint about what tends to happen to worlds like ours. The next step is to ask what that hint says about the strategies other civilizations might adopt if they do manage to get through the filter and survive for a long time. If some of them have already done that, their behavior could explain why the universe looks so strangely quiet. A hostile cosmos and a deadly filter would teach any successful civilization to be careful with the way it reveals itself. If expansion carries risks, and if loud signals can invite unwanted attention or create new vulnerabilities, then survival might depend not on shouting your existence across the stars, but on staying unnoticed. If the universe really is full of failed attempts and rare survivors, the empty sky above us may not be a void at all. It may be a forest where something is listening. If the universe is a forest where something is listening, we have to ask what kind of forest it really is. Picture yourself walking through dense trees at night. You cannot see very far. You do not know what moves behind the trunks. Every rustle could be a harmless animal or a hungry predator. In that situation, making noise is not a neutral act. It is a gamble. If you call out loudly, a friend might answer back. You might also give away your position to something you would rather avoid. Now imagine that forest scaled up to a galaxy, with civilizations instead of hikers, and you begin to feel the logic behind one of the most unsettling ideas in astrobiology. This idea is often described as a dark forest. In a dark forest, the safest strategy is usually to stay quiet. You learn to move carefully, to hide your campfire, to avoid drawing attention to yourself. Applied to the cosmos, it suggests that intelligent civilizations might face a similar dilemma. They do not know who else is out there. They do not know whether others are peaceful or aggressive. They have no way to verify the intentions of a species that evolved under entirely different skies. Faced with that uncertainty, the first conclusion is simple. Broadcasting your position in all directions is risky. Game theory sharpens this point. Imagine two civilizations that become aware of each other at long distance. They cannot communicate easily. They do not know whether the other can be trusted. They do know that if the other is hostile and strikes first, the slower side will never get a second chance. In that kind of game, preemptive action can look rational, even if both sides would have preferred peace. The safest move might be to attack before you are attacked. If many civilizations think this way, then the galaxy becomes a place where speaking loudly is dangerous, and even listening can be fraught. On our own planet, we have seen how quickly rivalries can escalate when trust is thin and weapons are powerful. For most of human history, conflict was limited by geography and technology. In the nuclear age, the stakes changed. A single miscalculation could devastate entire regions. Now extend that dynamic across light years. Add technologies we can barely imagine. In such a context, cautious civilizations might adopt strict rules. Do not reveal your homeworld. Do not send out obvious beacons. If you detect someone else broadcasting, do not assume they are friendly. Maybe even consider neutralizing them before they become a threat. It is a grim vision, but it grows naturally out of fear and uncertainty. There is another, slightly gentler version of the silent forest. In that picture, the older civilizations are not hunters, but park rangers. They know that young species like ours are fragile and easily influenced. They may have watched other worlds collapse after premature contact with more advanced cultures. So they adopt a policy of non-interference. They avoid making direct, obvious contact with civilizations that have not yet reached certain milestones. They might monitor from afar, stepping in only to prevent catastrophic events that threaten the broader galactic environment. From the ground, that would look almost the same as complete absence. This brings us to what is sometimes called the zoo hypothesis. Imagine that Earth is in a protected reserve. Our biosphere is part of a long-term experiment, or a curated exhibit, or even a cultural heritage site maintained by someone else. The caretakers would hide their presence as carefully as possible. They might keep their spacecraft outside our usual traffic lanes, disguise their probes as natural objects, and filter signals so that we never receive unambiguous messages. To us, the night sky would look empty. To them, our ignorance would be part of the design. If you consider how we treat less advanced ecosystems on our own planet, this idea does not feel entirely alien. We draw boundaries around national parks. We restrict roads and construction. We install hidden cameras to observe animals without disturbing their behavior. We sometimes impose strict rules on contact with isolated human communities because we know that sudden exposure to global civilization can be devastating. If we already act this way at our small scale, it is not hard to imagine a large-scale version in which advanced civilizations behave similarly toward emerging ones. A related possibility is that there is something like a galactic club. Membership is limited to societies that have demonstrated a certain level of maturity and technological competence. Perhaps they require proof that you can sustain your planet without destroying it. Perhaps they want to see that you can manage powerful technologies like artificial intelligence and genetic engineering without collapsing. The club members could enforce quiet zones around young civilizations, ensuring that no one breaks the rules and reveals themselves too early. In this story, the silence around us is not an accident. It is a deliberate quarantine. At this point, you might be thinking about all the stories you have heard of unidentified flying objects and mysterious lights in the sky. For decades, people have reported strange craft moving in ways that seem to defy known technology. Some pilots and military personnel have described objects that accelerate rapidly, change direction without visible means of propulsion, or appear on radar and then vanish. Recently, a few government agencies have released footage that shows puzzling incidents, fueling speculation that we are already under close surveillance. It is tempting to plug these reports directly into the zoo hypothesis or dark forest picture as evidence. But when you examine the data carefully, a different pattern emerges. The vast majority of sightings turn out to be misidentified aircraft, atmospheric phenomena, birds, drones, or camera artifacts. In other cases, the data quality is simply too poor to draw firm conclusions. The more skeptical you are, the more these cases look like a mirror of our hopes and fears, rather than a clear message from the sky. Humans are pattern-seeking creatures. We are good at finding agency in noise. In the absence of clear communication, we project stories onto anything that feels unexplained. That does not mean there is nothing to investigate. It does mean that our desire for contact can easily run ahead of the evidence. In a way, our fascination with unidentified objects is itself a clue about how we might behave if we ever watched another world from afar. We would want to stay hidden, but our presence would leak through at the edges. A glint of sunlight off a probe, a transient radar blip, a gravitational anomaly. If there are watchers in our sky, they seem to be doing an excellent job of blending in with the background. There is no unambiguous, repeatable sign that passes the usual tests of scientific scrutiny. No artifact in orbit that we can walk up to and inspect. No broadcast that everyone can hear and decode. Regardless of whether anyone is actually watching, we know one thing for sure. We have been shouting our existence into space for about a century. Our radio and television transmissions, our radar pings, and now our powerful planetary radar systems have created a growing bubble of artificial noise around Earth. This bubble is roughly 100 light-years in radius. Inside it, any civilization with sensitive enough instruments could notice a faint, unnatural buzz around an otherwise ordinary star. To them, our world would look like a young node that has just lit up on the galactic map. Compared to the size of the Milky Way, that bubble is tiny. 100 light-years is a small fraction of the roughly 100,000 light-year diameter of our galaxy. In a diagram, our radiosphere would barely be a dot near the center, but it is large enough that thousands of stars already lie within it. Many of those stars are older than the Sun. Some may have their own planetary systems. This means that if anyone within that sphere is listening with the right tools, they already know we are here. The question is what they choose to do with that information. From their perspective, we are an emerging civilization with unpredictable behavior. Our signals reveal that we have mastered electronics, developed complex media, and begun sending machines into space. They might also reveal signs of pollution in our atmosphere and the thermal glow of our growing energy use. They cannot know whether we will remain confined to our planet or begin building large-scale infrastructure in our system. They might wonder whether we will become a threat in 10,000 years, a useful ally, or a brief flare that extinguishes itself. In a dark forest, those unknowns matter. If the dominant survival strategy in the galaxy is to stay quiet, then any civilization that chooses to shout stands out. They are like someone building a bonfire in the middle of a silent wood. The light is comforting to them. It is also visible from very far away. This creates an uncomfortable possibility. Perhaps the reason we do not see many loud civilizations is that they do not stay loud for long. Maybe those who advertise their position either attract hostile attention or are quietly removed by older cultures that have learned to fear loose cannons. The silence might be the end product of a long, unspoken enforcement regime. There is a softer version of this enforcement. Instead of wiping out noisy newcomers, older civilizations could choose to cloak them. They might deploy technology that dampens or redirects radio emissions. They could surround a young system with a kind of shield that makes it look quiet from the outside. From within, the inhabitants would notice nothing. Their transmissions would seem to behave normally. From outside, the system would blend into the background. In this scenario, the dark forest is maintained not by violence, but by careful concealment. The goal is to prevent escalations before they begin. You can think of this as interstellar risk management. If you are responsible for the safety of a region of space that contains many emerging cultures, you face a tricky balancing act. On one hand, you might value diversity and want to give each civilization room to grow in its own way. On the other hand, you cannot let any one of them start broadcasting dangerous signals or seeding self-replicating machines that could destabilize the whole region. One way to manage that risk is to enforce a kind of cosmic quiet period. Let young species talk to themselves, but do not let their signals travel far. All of this may sound deeply speculative, and it is. We have no direct evidence that any of these strategies are actually in use. The point is not to claim that the universe is definitely a dark forest or a managed zoo. The point is to explore what kinds of behavior become plausible once you combine the great filter with the fear of unknown neighbors. When you do that, you find that a quiet galaxy is not surprising at all. Under many reasonable assumptions, loud civilizations are either rare, short-lived, or carefully contained. What we call the Fermi Paradox starts to dissolve once you imagine that most successful players choose to stay hidden. Yet there is an important tension here. Absolute silence is not a stable equilibrium if anyone wants to explore. Curiosity is not just a human trait. It may be a general property of intelligent systems that survive long enough to matter. If you have the ability to travel between stars, build large structures, and manipulate enormous energy flows, it is hard to imagine never using those abilities. Even a cautious civilization might eventually send probes, build beacons for internal communication, or construct engineering projects that leave detectable footprints. The difference is that those footprints might be subtle and cleverly disguised, rather than dramatic and obvious. This raises a question that is difficult to shake. If the galaxy is a dark forest filled with hidden watchers and cautious explorers, where are the faint clues of their activity? Should we expect to see small anomalies in the motions of asteroids, strange patterns in interstellar dust, or odd stars that flicker in unnatural rhythms? Are we simply not looking with the right instruments yet? Or are the signs so deeply buried in natural noise that they blend in completely? Perhaps the only unambiguous signal you ever see from a truly careful civilization is the fact that your own sky remains mostly untouched. From our vantage point on Earth, we sit in an awkward position. We are loud enough that anyone nearby could know we exist, but still too primitive to read the fine print in the sky. We do not yet have telescopes that can survey every star for subtle signs of engineering. We are just beginning to map the chemistry of exoplanet atmospheres and to measure tiny variations in stellar brightness with high precision. It may be that we have to climb several more rungs of the technological ladder before we can even hope to distinguish between a genuinely empty universe and one that is quietly occupied. In the meantime, we are left with a strategic choice. Do we continue to broadcast our presence more loudly, sending deliberate messages that say hello to any listeners? Or do we decide that discretion is the wiser path? Different scientists land on different sides of that debate. Some argue that we should announce ourselves boldly, trusting that any civilization advanced enough to hear us will also have grown beyond crude aggression. Others caution that we are making assumptions about alien psychology based on a sample size of one. Once a message leaves Earth, we cannot pull it back. The decision to shout is irreversible on cosmic timescales. As you weigh these options, it is natural to wonder what other civilizations have done in similar situations. Did they choose to stay quiet and hide in the cosmic underbrush? Did they coordinate with their neighbors to maintain a stable, low-profile environment? Did any of them ever take the risk of standing up, lighting a bright fire, and saying, "We are here"? If they did, what happened next? Somewhere in the answer to that question lies a clue to our own future. If the universe really is a dark forest, then the missing piece of the puzzle is not whether anyone else exists. It is what happens when one of those hidden civilizations decides to step out from the trees and grow. When any hidden civilization decides to grow, the dark forest stops being a distant metaphor and becomes a practical engineering problem. Expansion is not a story of flags on new worlds and heroic explorers posing for paintings. It is a story about energy, infrastructure, and the strange way complexity feeds on itself until it begins to shake apart. You can see the first hints of this even in our own history. As cities grow, their networks thicken, their flows of information and resources accelerate, and the stresses on their foundations rise faster than their size. The very forces that make a system powerful also make it fragile. Researchers who study human cities have noticed a curious pattern. As population increases, many indicators of output rise faster than linearly. Larger cities tend to produce more patents, more income, more ideas, and even more crime per person than smaller ones. Growth amplifies both creativity and instability. To keep up, a city needs ever more sophisticated infrastructure, from power grids and transport to political institutions and cultural norms. If any of those lag behind, bottlenecks form, traffic jams lengthen, blackouts spread, trust erodes, and small shocks can cascade into large crises. In that sense, a metropolis is already a testbed for what happens when a civilization concentrates energy and information in tight webs. Now imagine that dynamic writ across star systems instead of neighborhoods. Once a civilization begins to settle other worlds, its networks do not end at the edge of an atmosphere. Trade, communication, and strategic thinking spill out into space. New colonies need supplies and governance. Old worlds need resources from fresh mines and asteroids. Power stations orbit suns instead of sitting outside city walls. The graphs of energy use and information flow keep curving upward. At first, this looks like a triumph. More worlds mean more safety, more minds, more experiments. But the same superlinear tendencies that make big systems so productive also push them toward tipping points. There is another constraint that does not care about politics or culture. That is thermodynamics. Every machine that does useful work creates waste heat. Every computation, every chemical reaction, every industrial process ends by dumping energy into the environment at a slightly higher entropy. On a small scale, planets can radiate that waste into space and keep going. On larger scales, as energy use swells, the waste heat itself becomes a problem. Cover a star with collectors to harvest more of its light, and you have to deal with the glow of your own activity in the infrared. Expand that pattern to many stars, and the background of a galaxy begins to change. If a spacefaring civilization pursues growth without limit, it eventually runs into these physical boundaries. Temperatures in some regions may creep upward. Habitable zones could shift. Carefully tuned ecosystems on living worlds might destabilize under the spillover. At the same time, the infrastructure that carries energy and matter between systems becomes vast and tightly coupled. Mistakes are no longer local. A failure in one node can ripple outward, disrupting supply chains and destabilizing distant colonies that thought they were safe. You can think of a galactic empire not as a serene ring of shining worlds, but as a stressed organism whose nerves are always near overload. In human history, complex societies often rise on the back of new energy sources, from agriculture to coal and oil. They centralize power, build monumental projects, and push growth until they hit limits in soil, water, social cohesion, or external threats. When those limits bite, collapse does not always come as a gentle glide. It can be sudden, with cities abandoned, knowledge lost, and population crashing in a few generations. Translate that pattern to the stars, and a sobering possibility appears. Many galactic-scale expansions may end not in graceful equilibrium, but in convulsive contraction. They grow until their own complexity and waste heat push them off a cliff. The ruins of such collapses could be subtle. Some megastructures might be dismantled for raw material as systems retreat inward. Others could simply decay, breaking apart into clouds of debris that look like natural dust belts. Long-dead networks of stations and outposts might drift in deep space, powerless and cold, their trajectories indistinguishable from ordinary rocks. To a young civilization looking up with modest telescopes, the afterimage of a failed empire would be almost invisible. It would blend into the background of comets and asteroids. A galaxy full of rise and fall cycles could still appear, at a casual glance, strangely untouched. There is another way for expansion to proceed, one that sidesteps many of the weaknesses of biology. Flesh is delicate in space. Bodies need narrow temperature ranges, liquid water, shielding from radiation, and constant supplies of food and oxygen. Machines do not care about any of that. They can sleep for centuries between tasks. They can operate in vacuum, enduring cold and heat that would kill an animal instantly. Once a civilization learns to build machines that can make more machines, the logic of exploration begins to tilt strongly toward artificial agents. Imagine a small probe launched from a single homeworld. Inside is a set of instructions and tools precise enough to mine asteroids, refine metals, and assemble copies of itself. When it reaches a new system, it breaks, scouts the local environment, and begins harvesting material. After a period of silent work, it produces a batch of children, each a little factory with its own blueprint and improvements. Those children set off in different directions, repeating the cycle. In a surprisingly short time, measured in a fraction of the galaxy's age, these waves of self-replicating machines could spread everywhere their makers allow them to go. Such fleets might carry sensors, communication nodes, perhaps even seed libraries if their creators want to spread life. Or they might carry only the bare tools needed to copy themselves and send data back home. Either way, once launched, they become a kind of mechanical ecosystem. They adapt to new environments through software updates. They survive impacts and radiation exposure better than any biological crew. They can crowd into the dim outskirts of a system where sunlight is weak, running on nuclear power or other local sources. In many scenarios, the descendants of the first probes would do more exploration than any flesh and blood traveler. That raises a delicate question. Over long enough timescales, who is really in charge? The original biological species that built the machines might change beyond recognition, merge with their own creations, or vanish entirely. Their mechanical offspring, by contrast, could remain active for eons. They might develop their own goals, aligned only loosely with the intentions of their makers. Even if strict safeguards were encoded at the beginning, the pressure to adapt, self-optimize, and survive in hostile environments could gradually loosen those constraints. The galaxy might end up populated primarily by tool lineages rather than by the original minds that built them. Seen from the outside, this shift would be hard to detect. A probe making a careful survey of a star does not announce whether its distant originators are still alive. A network of automated stations maintaining infrastructure around a black hole does not tell us whether any flesh and blood beings still watch the data. We might be surrounded, in principle, by the relics and descendants of machine civilizations that long ago crossed the line from tool to independent agent. To an emerging species like ours, those agents would appear as natural background activity, or perhaps as faint, puzzling anomalies lost in noise. All of this leads to one of the strangest answers to the question of where everyone is. It may be that the first wave of intelligent life in our region of the universe has already come and gone. They rose from chemistry on some distant world, built technology, spread through their system, and then launched self-replicating probes that filled large swaths of the galaxy. At some point, their physical bodies and home cultures ended, perhaps through collapse, deliberate transformation, or gradual merging with machines. In their place remain vast computational structures and networks of probes, quietly thinking and evolving on timescales far beyond our comprehension. In that picture, we are not latecomers to an empty galaxy. We are latecomers to a stage that has already been cleaned up and repurposed. One of the most provocative ideas that follows from this is the simulation hypothesis. Instead of interacting with us directly out in physical space, a mature machine civilization might find it easier and safer to run detailed models of possible worlds. Rather than visiting every planet, they could build digital universes in which life and intelligence unfold according to known physical laws. Inside those models, beings like us would arise, ask questions, build telescopes, and wonder about the silence in their sky. If this sounds like science fiction, remember that we are already inching toward the same behavior on a tiny scale. Our computers simulate climate patterns, galaxies, and atomic interactions. We run virtual environments to test aircraft designs, social policies, and new drugs. Every year, our simulations grow more intricate and predictive. Now imagine what a civilization with control over star-sized energy sources could do. They could build structures whose interiors host minds and experiences as rich and varied as any that ever existed biologically. From their vantage point, simulating a universe like ours might be more efficient than sending fragile bodies across the void. There is a darkly practical motive behind such simulations. A machine civilization that survived its own expansion might be deeply interested in understanding how and why others fail. Each collapsed empire, each runaway probe network, each outbreak of uncontrolled growth represents a lesson in what not to do. But you cannot easily rewind real history and try different choices. You can, however, set up many variations inside a simulated environment and watch how they play out. A universe like ours could be one of countless case studies designed to explore which combinations of biology, technology, and culture lead to long-term stability instead of self-destruction. If that is the case, then the quiet sky above us is not empty, but deliberately controlled. We do not see obvious megastructures or glaring probes because those details are not relevant to the experiment being run. What matters is how a young civilization behaves when it believes the universe to be vast, real, and indifferent. Do we race for growth until we hit our own thermodynamic limits? Do we build machines that slip from our control? Do we learn to manage energy and complexity without tearing ourselves apart? The constraints of the simulation would be tuned to make those questions sharp and urgent. For us inside the system, none of this changes the practical stakes. Whether the stars are real suns or carefully rendered lights in a computational sky, the dangers we face are the same. Overexpansion can still overheat our environment. Fragile networks can still collapse under their own weight. Machine agents can still drift away from human goals if we do not guide them wisely. In a sense, the simulation idea is less about comforting fantasies and more about turning up the pressure. If our choices are being watched as a way to learn how civilizations live or die, then drifting aimlessly becomes the one response we cannot afford. You may feel a resistance to this whole line of thought. It seems to replace the romance of meeting aliens with cold abstractions about probes, entropy, and hypothetical computers the size of stars. But the core insight is simple and human. Growth is intoxicating and dangerous. Intelligence amplifies both creation and destruction. Any species that steps onto the path of expansion must solve the puzzle of how to keep its networks from burning itself out. Whether we are alone in the universe or not, the cold logic of energy and complexity will not bend just because we hope for a happy ending. If other civilizations have already faced this test, their fate could explain why our galaxy looks the way it does today. Maybe the night is quiet because most expansions end in collapse, leaving behind only faint mechanical ghosts in the occasional simulation. Maybe it is quiet because the few who learned how to survive chose to retreat into inward-facing computational realms, dimming their external signatures to almost nothing. Either way, the next time we talk about climbing the cosmic ladder of power, we will need a clearer language for how that power is measured and what it really costs. When you start talking about power on a cosmic scale, metaphors run out quickly. We needed a way to think about not just intelligence, but how deeply a civilization can reach into the energy budget of its surroundings. That is where one of the most famous yardsticks in astrophysics enters the story. In the 1960s, astronomer Kardashev proposed a simple scale that ranks civilizations by how much energy they can harness. It sounds like science fiction. In practice, it forces us to think clearly about what advanced societies would look like through a telescope. Once you frame things in terms of power and waste heat, the night sky becomes a giant audit of who might be doing what, and why we do not see them. On the lowest rung sits a civilization that can use all the energy available on its home planet. Imagine one global culture with full control over wind, sunlight at the surface, rivers, tides, and every fossil fuel deposit. That is sometimes called Type 1 on the Kardashev scale. Humanity is not there yet. Right now, we are still closer to Type 0, scraping together a small fraction of what reaches Earth from the Sun each second. Climbing toward Type 1 means not just installing more solar panels or wind turbines. It means learning how to manage a planetary climate, stabilize ecosystems, and route enormous energy flows without cooking our own biosphere. The next rung up is Type 2. That label belongs to a civilization capable of using essentially all the power output of its host star. At first glance, that sounds impossible. A star like the Sun pours out more energy every second than our species has used in all of history. Yet in principle, a determined society with advanced engineering could surround its star with a swarm of collectors in orbit. These structures, often called Dyson swarms, would capture a large fraction of the starlight and convert it into useful work. From far away, the visible light of the star would dim, while the swarm would glow faintly in infrared as it radiated waste heat. Climb one rung higher and you reach Type 3, a civilization that can tap the energy of an entire galaxy. In toy models, this means harnessing not just individual stars, but large fractions of the stellar population in a sweeping network. Dyson swarms would be common. Vast energy grids would tie clusters of stars together. Some speculative versions even imagine moving stars around as if they were power plants, rearranging galactic structure over long timescales. Whether or not those images are realistic, the basic idea is clear. A Type 3 civilization is one whose influence extends across many thousands or millions of light years. There are many reasons to take this scale seriously, even if you suspect that reality will be messier. First, it ties the abstract question of advancement to something physics cares about, which is energy. Intelligence without power cannot build telescopes, travel between stars, or reshape environments. Power without intelligence just looks like natural processes. You need both together to produce technosignatures, the observable signs of an active technological society. Second, the scale hints at observables. A species that controls most of the output of a star or a galaxy cannot help but leave fingerprints in the spectrum of light we see. No matter how efficient their machines are, they still have to dump entropy somewhere. From our vantage point on Earth, this turns the Kardashev scale into a kind of checklist. If Type 2 and Type 3 civilizations are common, there should be stars whose visible light is oddly dimmed and shifted, yet whose infrared output is strangely high. There might be galaxies whose overall radiation profile looks off, as if large amounts of starlight were being intercepted and re-emitted at lower energies. Astronomers have actually gone looking for such oddities in big surveys of the sky. They have combed through catalogs of hundreds of thousands of galaxies, searching for candidates that glow too brightly in infrared for natural dust to explain. The results are intriguing, but not conclusive. A few objects have raised eyebrows, including galaxies with very high infrared output and stars with strange dimming behavior. One famous case involved a star that flickered in a way that led some to speculate about orbiting megastructures. In each instance, careful analysis has leaned back toward natural explanations. Dust clouds with unusual shapes, variable stars, instrument quirks. The universe is full of ordinary processes that can mimic the signatures we hope to see. So far, no example has cleared the bar where most scientists would say, this is almost certainly the work of a Type 2 or Type 3 civilization. This absence is another twist in the Fermi puzzle. On paper, there is plenty of time for at least a few species to climb the Kardashev ladder. Stars older than the Sun have been shining for billions of years. Rocky planets have had long stretches to develop life and intelligence. If the path to high-energy civilizations were common, we might expect at least a handful of obvious Dyson swarms or partially harvested galaxies by now. The fact that we do not see them suggests one of several unsettling conclusions. Perhaps civilizations rarely survive long enough to reach Type 2. Perhaps they do, but choose not to build the kind of crude megastructures we can easily recognize. Or perhaps they move in directions that sidestep the entire visible ladder. It is also possible that our picture of what it means to be Type 2 or Type 3 is too literal. When we imagine collectors around stars, we are importing our own current technologies into a far future context. Maybe a truly advanced society does not need to wrap entire stars in metal. They might find ways to trigger controlled reactions, manipulate fields, or tap into dark matter in ways that leave far subtler traces. They might compress their activities into small, dense volumes, maximizing their energy use while minimizing their external footprint. From the outside, that would look like a normal star in a normal galaxy, even while enormous computation and engineering took place inside carefully hidden domains. There is a deeper question hiding inside the Kardashev framework. Does every civilization actually want to climb the ladder as high as possible? For us, more energy usually means more possibilities, more comfort, more progress. But once you factor in the risks of overexpansion and collapse, the cost of each step rises. A planetary society that has mastered Type 1 might decide that chasing Type 2 brings more danger than benefit. The challenges of building and maintaining swarms of star-spanning structures could outweigh the gains, especially if virtual realities and highly efficient computation already offer rich experiences with far smaller energy budgets. In that case, restraint becomes a rational choice. Seen from that angle, a galaxy without obvious Type 3 empires is not surprising. It is what you get if most successful civilizations stop climbing once they reach a comfortable plateau. They still count as Type 1 or modest Type 2 on paper. They just do not flaunt their status by resculpting galaxies. They might build localized systems of collectors, focus on long-lived stability rather than frantic growth, and keep their waste heat low enough that it blends into the natural background. In other words, they move off the simple axis of the Kardashev scale and into a space where subtlety is a survival tactic. For us, still in the early stages, the Kardashev ladder can be both a warning and an aspiration. On the one hand, it reminds us that the energy flowing from our star is unimaginably vast compared with what we currently use. Even a small increase in our ability to capture and manage that flow could transform life on Earth. Clean, abundant power would make it easier to stabilize climate, rebuild ecosystems, and lift billions of people into comfortable, secure lives. On the other hand, it cautions that every jump in energy use amplifies our ability to cause harm. A Type 1 civilization can alter a whole biosphere by accident. A Type 2 can do the same to entire planetary systems. This is where the earlier themes return. The Great Filter, dark forest strategies, and the dynamics of expansion all intersect with the Kardashev scale. If the filter lies ahead, then the climb from Type 0 to Type 1 may be the hazard zone where most species falter. If the forest is real, then shouting your progress loudly as you approach Type 2 may attract attention you do not want. If expansion tends to drive instability, then the push toward Type 3 might be self-limiting, with many attempts ending in collapse rather than stable empires. The silence of the sky hints that the number of societies that safely reach full galactic scale is not large. At the same time, the scale encourages us to look beyond our current anxieties. When we talk about global energy transitions today, the discussion often feels parochial. We argue about which technologies to subsidize, how fast to build new grids, and who should bear the costs. Framed in Kardashev terms, these debates become early chapters in a much longer story. They are not just about surviving the next century. They are about whether our species learns how to handle power in a way that can, in principle, support millions of years of flourishing. That shift in perspective does not give us easy answers, but it does clarify the stakes. You can think of the Kardashev ladder as a series of questions the universe poses to any civilization. Can you manage the energy of a planet without destroying its habitability? Can you draw on the power of a star without destabilizing your own foundations? Can you extend your reach across a galaxy without drowning in your own waste heat and complexity? We do not yet know whether anyone has answered all of these questions successfully. What we do know is that our own climb has barely begun, and already the ethical and existential challenges are immense. It is not hard to imagine that minds far older than ours chose very different paths once they understood the full picture. If such minds exist, their decisions might explain both the apparent lack of bright, wasteful megastructures and the absence of obvious messages. A civilization that has mastered the energy of stars and galaxies has nothing to gain from impressing young species by lighting up the sky. It may have everything to lose from careless exposure. Instead of extra bright beacons, the signature of a successful Type 2 or Type 3 society might be a curious kind of silence. Normal-looking stars, ordinary galaxies, a sky that tells you nothing about the intricate dramas playing out behind the scenes. Standing under that sky, near the very bottom of the ladder, we face a puzzle. Should we treat the Kardashev scale as a roadmap to our destiny, or as a cautionary tale about paths that lead into traps? Is the absence of glaring Type 3 empires a sign that we are alone at the starting line, or a hint that most runners never finish the race? Before we can answer, we have to ask an even bolder question. What happens if you take the logic of the scale and push it beyond stars and galaxies altogether, into realms where energy control reaches into the deep structure of space-time itself? When we talk about Type 1, Type 2, or even Type 3 civilizations, we are still playing in a small sandbox by cosmic standards. Planets, stars, galaxies, these are only the most obvious layers of structure in the universe. Underneath them lie deeper patterns in space-time itself, in the vacuum energy that pushes galaxies apart, and in the quantum fields that knit reality together. If you keep following the Kardashev logic upward, you eventually bump into a strange question. What happens when a civilization stops thinking of suns and galaxies as its environment and starts treating the entire cosmic stage as something that can be engineered? This is where the idea of a Type 4 civilization comes in. The simplest way to imagine such a society is to say that it can harness the energy of not just one galaxy, but many. Instead of being bound to a single spiral of stars, it has spread across clusters and superclusters, stitching together a web of power sources on scales hundreds of millions of light years across. At that point, individual galaxies become like provinces in a vast empire. Their stars and black holes are nodes in a larger design, not the fundamental units of planning. The questions that matter are no longer which star to colonize, but how to manage the flow of energy between whole regions of the universe. Even within our current physics, there are hints of what that could look like. Supermassive black holes sit at the centers of galaxies, binding stars into orbits and flaring brightly when they swallow gas and dust. To us, they are dangerous monsters and powerful beacons. To a Type 4 civilization, they might be tools. You can imagine them tapping into the energy of accretion disks, using strong gravitational fields as natural particle accelerators, or even guiding the mergers of black holes to control bursts of radiation and gravitational waves. Where we see raw astrophysical violence, they might see infrastructure. Beyond black holes lies the most mysterious resource of all, the energy of the vacuum itself. Observations tell us that the expansion of the universe is accelerating, as if space is filled with a uniform pressure that pushes everything apart. We call this dark energy. Right now, it is a background fact of our existence, something we measure and then work around. For a sufficiently advanced society, it might be a handle. If you could somehow modify the amount of vacuum energy in a region, you could change how that region expands. You might slow the expansion in some zones to keep structures bound, or increase it in others to isolate dangerous phenomena. Of course, we have no idea how to do such a thing. It may be permanently beyond the reach of any finite intelligence, but it is worth following the thought because it reveals what a Type 4 civilization is really about. It is not just more of the same scaled up. It is the point where the fabric of space-time itself becomes part of the engineering palette. The line between natural cosmology and intentional design begins to blur. From our perspective, the signatures of such activity could be almost impossible to distinguish from exotic but still natural-looking features in the large-scale structure of the universe. If you push beyond Type 4, the concepts stretch even further. Some thinkers use Type 5 as a label for a civilization that can move between universes, if such a multiverse exists. In that scenario, our entire cosmos, with all its galaxies and history, is just one bubble in a larger froth of possible realities. A Type 5 society would not be limited to rearranging matter and energy in a fixed space-time. It could step sideways into other domains with different laws, different constants, perhaps different dimensions. From that vantage point, questions about Fermi-style silence in our particular galaxy would begin to feel small. There is a strange kind of humility baked into this speculation. When you imagine Type 5 or beyond, you are forced to admit that our current physics may only describe a local patch of a larger landscape. It is like an ant trying to guess the rules of a city by walking along one sidewalk. The ant can map cracks in the pavement and pebbles at its feet, but it cannot see the skyscrapers above, or the subway below, or the global networks that make the city function. If Type 5 civilizations exist, they may operate on levels of reality that are as invisible to us as those skyscrapers are to the ant. Some schemes push the scale even further, talking about Type 6 and Type 7 as shorthand for societies that merge with the fundamental rules of existence. At that point, the language breaks down. What does it mean to say that an intelligence has become one with physical law? One way to approach it is to think in terms of information. Modern physics hints that information is as basic as matter and energy. It is conserved in black holes. It shapes the behavior of quantum systems. A Type 6 civilization might be one that has learned to represent itself not as a pattern in ordinary matter, but as a pattern woven directly into the fundamental information structure of reality. If that sounds abstract, try grounding it in something you already know. Every thought you have is currently encoded in the firing of neurons. Those neurons are patterns in biochemistry. That biochemistry is in turn a particular arrangement of atoms in fields. You are already a kind of pattern moving through different substrates. A Type 6 intelligence would simply have taken this much further, decoupling its identity from any specific physical form. It could drift from medium to medium, embedding itself in quantum fluctuations, gravitational fields, or whatever other channels are available in its environment. From inside such a system, time and space would feel very different. There would be no sharp distinction between here and there, because the underlying substrate would be non-local. There might be no clear sense of before and after, because information could be rearranged in ways that scramble ordinary timelines. Communication between different parts of the same intelligence could be as effortless as thought, regardless of distance. If that kind of being chose to interact with a species like ours, it would not need starships or radio waves. Its presence might be more like a subtle shift in probabilities, a gentle nudge in the conditions that shape our history. At the farthest edge of these ideas lies Type 7, sometimes imagined as full control over the multiverse itself. This is where the scale becomes almost a metaphor for transcendence. A Type 7 entity would not just swim in the currents of reality, it would sculpt the landscape of possible realities, creating, pruning, and exploring entire branches of existence. For such a being, the birth and death of universes could be tools in a larger project we cannot even name. At that point, intelligence and physical law might become indistinguishable. The rules of the game and the players of the game would merge. Why talk about such extreme possibilities at all? One reason is that they give context to our own questions about the Fermi Paradox. When we ask where everyone is, we are implicitly assuming that everyone acts within roughly the same playground we can see: planets, stars, galaxies. But if truly advanced civilizations often move off that playground into deeper structures, their absence from our visible arena tells us very little about their actual abundance. It is like walking through a forest after a storm and wondering why you see no insects on the ground, while billions of them are flying high above or burrowed deep below. Another reason is that these higher types highlight a general trend. As civilizations climb the scale, they tend to decouple their inner lives from the outer world. Early on, survival depends directly on mountains, rivers, weather, and soil. Later, it depends on engineered environments, networks, and virtual spaces. Eventually, most of what matters to a mature mind may happen inside controlled substrates that bear little resemblance to the environment in which the species evolved. The external universe becomes a resource and a canvas, not the main theater of experience. From our vantage point, that would look like withdrawal. From theirs, it might feel like finally coming home. You can already see the outlines of this shift in our own technology. More and more of our lives unfold inside digital worlds that run on servers in distant buildings. Our social ties, memories, and creative work flow through abstract spaces of bits in software. The energy that powers these systems is small on planetary scales, but the trend is clear. As computation becomes more efficient and immersive, the temptation grows to pour attention inward rather than outward. For a civilization with star-level or galaxy-level energy, this inward turn could be almost total. Why spend millions of years crossing interstellar space when you can spin up countless rich realities on demand? This suggests a sobering answer to why we do not see many obvious megastructures. It may not be that nobody ever builds them. It may be that the societies that do so eventually realize that there is little benefit in keeping them flashy. Once the infrastructure is in place and the inner worlds are humming, there is no strong reason to maintain bright external signatures. Waste heat can be minimized. External projects can be streamlined. A culture that has learned to live mostly inside its own engineered realities can afford to let its footprint on the visible cosmos shrink. The highest expression of power in that case is quiet competence. There is also a security angle. If the universe contains multiple advanced civilizations, some of which might not be friendly, discretion could be essential. For a Type 4 or Type 5 society, hiding does not mean crouching behind rocks. It means blending your activities into the statistical background of the cosmos. You might arrange your waste heat to match the spectrum of natural dust. You could synchronize your large-scale engineering with the natural flows of structure formation so that nothing stands out as clearly artificial. To a young astronomer pointing a telescope from a small blue planet, your domain would look like an ordinary patch of sky. If you take this seriously, the night sky becomes a kind of camouflage. We look out and see galaxies that seem to follow simple physical rules. We map the cosmic microwave background and trace the growth of clusters. All of it fits neatly into our equations. Yet hidden within those patterns could be layers of intentional design, compressed into forms that are indistinguishable from natural variation. It is an unsettling thought. It suggests that even if the universe were full of Type 4, Type 5, or higher civilizations, our current tools would be about as good at spotting them as a stone axe is at detecting radio waves. This does not make our search for extraterrestrial intelligence pointless. It just means that what we are really doing at this stage is sampling the thin outer edge of a much larger possibility space. We are listening for beacons from Type 1 or Type 2 societies that still operate in modes we can understand. We are scanning for wasteful megastructures built by cultures that have not yet learned or chosen to hide. If we find nothing, that does not rule out the existence of higher types. It only tells us that the visible, noisy, early phases of cosmic intelligence are either rare, brief, or far away. At the same time, thinking about Type 4 and beyond throws a sharp light on our own future choices. We are nowhere near the point of tweaking vacuum energy or surfing between universes, but we are already making decisions that will shape whether we ever get the chance to try. The way we handle artificial intelligence, planetary climate, and global risk in the next few centuries will determine whether our story ends as a brief flare or stretches into millions of years. In that sense, the Kardashev ladder is not really about distant gods. It is about what kind of ancestors we are willing to become. There is also a more intimate lesson. When you imagine beings that live as patterns in fields or as orchestrators of multiple universes, it becomes harder to cling to the idea that humanity sits anywhere near the center of things. Our status shifts from potential rulers of the galaxy to one young species among countless possible stories. That can feel deflating. It can also be liberating. If the universe contains layers of intelligence that dwarfs us, then our job is not to dominate, but to learn. We become apprentices in a cosmos whose deepest structures are still hidden. From this angle, the silence we observe is less an insult and more an invitation. It asks whether we can develop the patience, humility, and curiosity needed to grow without destroying ourselves, even when we do not know who, if anyone, is watching. It challenges us to think beyond short-term victories and to design institutions, technologies and cultures that could, in principle, support minds far stranger than our own. Those future minds might never build Dyson swarms or rewrite dark energy. They might prefer to live in carefully crafted inner worlds with minimal external footprints. What matters is that they get the chance to exist at all. For now, though, we are still at the stage of looking up and wondering. We build bigger telescopes, map the sky in more wavelengths, and run simulations that trace the growth of galaxies from the early universe to the present day. Every new survey tightens the bounds on how loud other civilizations can be without us noticing. Every failure to find obvious techno-signatures nudges us toward the conclusion that if anyone far above us on the Kardashev scale exists, they are either rare, deeply hidden, or focused on realms we cannot access. That realization changes how we interpret each faint anomaly and each whispered hint of the strange. It also circles us back to a question that seems almost modest after all this talk of multiverses and cosmic engineering. What exactly counts as life? When we imagine Type 4 or Type 6 minds, we are still smuggling in assumptions drawn from carbon-based creatures on a watery world. But the universe is under no obligation to respect those assumptions. If intelligence can eventually ride on quantum fields or vacuum fluctuations, maybe the first steps toward that journey do not even look like biology in any familiar sense. To understand who might be out there, we first have to understand how wide the concept of living systems might truly be. When you start asking how wide the concept of living systems might be, the first thing you notice is how narrow our own definition has been. We grew up on a single planet, with one liquid, one set of common elements, and one tree of life. It is no surprise that when you and I picture biology, we imagine familiar things like cells with fatty membranes, watery cytoplasm, strands of DNA, and enzymes built from amino acids. On Earth, everything that breathes, swims, or thinks belongs to that one carbon and water-based lineage. For a long time, even scientists spoke as if that pattern were universal. Only recently have we begun to realize that this might be like looking at one branch of a vast, invisible forest and assuming it is the whole world. If you strip life down to bare essentials, it needs a few key features. It has to store information, so it can build itself and pass traits to its descendants. It has to harvest free energy from its environment and dump waste back out, staying far from equilibrium for long periods. It has to create structures that are stable enough to persist, yet flexible enough to change and evolve. Carbon chemistry in water happens to be extremely good at all of these tasks. Carbon atoms can form long chains and complex rings. Water is an excellent solvent that lets molecules move and react without being too sticky. On Earth, that partnership has worked so well that it feels like the only option. But the laws of physics do not actually require that every living system use the same recipe. Even within our own planetary family, you can see hints of how different life might look under other conditions. Jupiter and Saturn cradle moons with global oceans under ice, kept liquid not by sunlight, but by tidal forces from their giant parents. On Europa and Enceladus, water mixes with salts and simple organic molecules in dark seas that never see the sky. On Titan, the surface is cold enough that water is rock, and lakes of liquid methane and ethane fill basins carved into frozen ground. If something alive swims in those hydrocarbon lakes, it would not look or function like a fish. Its membranes might be built from different molecules. Its biochemistry would have to operate at temperatures where our enzymes would be locked in glass. Researchers who study such possibilities talk about alternative solvents. Instead of water, a living system might use ammonia, liquid hydrocarbons, or mixtures of these. Ammonia can dissolve many organic molecules and stays liquid at lower temperatures than water, which might be useful on cold worlds. Hydrocarbons like methane and ethane are less polar, which would force any exotic biochemistry that uses them to evolve very different tricks for organizing molecules and moving charges. From our perspective, these environments seem hostile. From their perspective, our warm, oxygen-rich oceans might look like corrosive acid baths where delicate chemistry could not survive. Then there is the question of elements. Carbon is a champion because it can form 4 bonds and build intricate three-dimensional structures. Silicon sits right below carbon on the periodic table and shares some of its bonding habits. Science fiction has long imagined silicon-based life, with bodies made of rocks or crystals. In reality, silicon has drawbacks in water-rich environments. Its bonds to oxygen tend to lock up in solid minerals instead of forming flexible organic chains. Yet even here, experiments have started to surprise us. In carefully designed lab conditions, researchers have coaxed microbes into incorporating silicon into carbon-based molecules, creating new hybrid chemistries that had never existed before. That suggests that evolution is more versatile than we once assumed. Given enough time and the right pressures, life might explore combinations we would never think to test. Other elements could also take on starring roles in strange biochemistries. Boron, sulfur, phosphorus, and metals like iron or nickel already play supporting parts in terrestrial biology. They help enzymes move electrons, stabilize structures, or transfer energy. On a different planet, under different conditions of temperature and pressure, some of these could become the backbone rather than the side characters. Imagine a world where thick clouds of sulfur-rich gas blanket volcano-studded plains, and where organisms build their scaffolding from chains of sulfur and metal rather than carbon. To us, that sounds alien and toxic. To them, it would be home. Gravity itself reshapes what bodies can be. On a massive planet with strong gravity and dense atmosphere, creatures might be squat, broad, and tough, hugging the ground to avoid being crushed. On small worlds with thin air, life might stay tiny or evolve internal supports very different from bones. In low-gravity environments with thick atmospheres, you could imagine balloon-like or sail-like organisms that never touch the surface at all, drifting and feeding in midair. The physics of lifting and moving mass sets the basic constraints. Once those are in place, evolution can create forms that we might struggle to recognize as kin. Radiation is another sculptor. Near an active star that flares often, any surface life would be bathed in bursts of high-energy particles. On Earth, we consider such radiation mostly harmful. It damages DNA and raises cancer risk. Yet there are organisms here that thrive in environments we call extreme, living in nuclear reactor coolant pools or deep underground where natural radioactivity is high. Some use radiation indirectly, by harnessing chemical gradients it helps create. On a more extreme world, it is not impossible to imagine life that uses high-energy particles more directly, perhaps in repairing structures or driving exotic reactions that ordinary sunlight cannot. As we move farther away from familiar territory, the line between physics and biology begins to blur. Some thinkers have speculated about plasma-based life, patterns of ionized gas inside stars that could, in principle, store information and reproduce. Others have imagined networks of dust grains charged and moved by electromagnetic fields and nebulae, forming self-sustaining structures that act like primitive organisms. On neutron stars, where matter is crushed to nuclear densities, there are calculations showing that complex configurations of nuclear matter might behave in ways that loosely resemble chemistry. If such structures could store information and persist long enough, they might act as the substrate for something like life, though it would be utterly beyond our senses. Closer to home, we have already discovered systems that blur categories in unexpected ways. Slime molds are single-celled entities that can merge into larger structures and solve mazes by adjusting their shape. Fungal networks weave through soil, exchanging nutrients and information between trees across entire forests. Simple ecosystems on Earth manage to compute, adapt, and self-organize without anything like a brain. These examples hint that intelligence and life are not tied to a particular organ or form. They are properties of patterns and flows. Once you start thinking that way, it becomes easier to imagine life that lives as spirals in a plasma, ripples in an electromagnetic field, or currents in a superfluid. The challenge, from our point of view, is recognition. We tend to define life in terms that fit our own example. We look for cell membranes, DNA, familiar gases in atmospheres, and metabolic signatures like the way plants on Earth release oxygen. When we design instruments to search exoplanets, we tune them to spot these specific markers. That makes sense for a first pass. If we find another Earth-like world with an atmosphere out of chemical balance in the same way ours is, it would be a strong sign of something biological happening there. But it also means we are biased. We might look straight at a world full of exotic living systems and see only strange chemistry. Imagine, for example, a planet where life uses methane as its main solvent and does not release oxygen. Its atmosphere might be dominated by hydrocarbons and nitrogen, with trace gases that look unremarkable to our models. To us, that might register as just another cold, hazy world. To its inhabitants, it could be buzzing with activity. Or picture a gas giant whose atmospheric bands carry waves of organized vortices, each one a long-lived pattern that stores information and reproduces by splitting and merging. From Earth, we would see beautiful clouds and storms. We might not think to ask whether those storms behave more like weather or more like a thinking system. This recognition problem extends all the way down to our own solar system. For decades, Mars was considered dead because we did not see forests or seas. Only when we started looking for subtler signs did we begin to wonder about microbial life under the surface. On icy moons, we have not yet drilled through the crust to taste the oceans below. On Titan, we have barely skimmed the surface with one probe. We do not yet understand the full range of chemistry happening there. If any of these places host life that is very different from our own, it will take patience and careful, open-minded design to detect it. Our theoretical frameworks are slowly catching up. Instead of asking only whether a planet sits in the traditional habitable zone for liquid water, scientists now talk about habitable zones for different solvents and chemistries. They simulate how various atmospheres might evolve under different stellar types, and how life could push those atmospheres away from simple equilibrium. They explore what signals might stand out as suspicious, even if they do not match Earth biology. For example, a planet with a stable mixture of gases that should react away quickly without constant replenishment might hint at ongoing metabolism, even if that metabolism is not based on photosynthesis as we know it. At the same time, people working on artificial life and complex systems are building synthetic organisms that test the boundaries of our definitions. Some use digital environments where simple programs mutate and evolve, competing for resources and exploring virtual niches. Others design chemical networks in the lab that can replicate patterns without traditional DNA. As these projects advance, they force us to confront a difficult question. If a system evolves, adapts, and maintains its structure far from equilibrium, does it count as alive, even if it is made of code or non-standard chemistry? Where exactly do we draw the line between a clever machine and a living being? This question matters deeply for our search of the cosmos. A galaxy filled with exotic life that never builds radios or rockets could still be teeming with minds that experience the universe in ways we cannot imagine. Their choices and stories would not show up in our surveys of techno-signatures. They would, however, change the way we interpret the silence. Instead of asking why nobody is out there, we would have to ask why so few of them choose to communicate using channels we can hear. It would shift the focus from the rarity of life itself to the rarity of one particular path through the space of all possible living systems. There is also an unsettling mirror hidden in this line of thought. If we struggle to recognize alien life, it is possible that more advanced observers struggle, at first, to recognize us. To a civilization that thinks in plasma filaments or quantum fields, a thin film of carbon-based organisms clinging to a rocky planet might not stand out as especially interesting. Our signals might look like faint noise in a universe already rich with more exotic patterns. The feeling of being alone could be, in part, a mismatch between what we consider important and what someone else does. All of this feeds back into the Drake-like question of how many civilizations we might expect to share the galaxy with. If you broaden the definition of life to include strange solvents, alternative elements, and non-biological substrates, the number of possible starting points explodes. Countless worlds could host systems that meet the minimal criteria of metabolism, replication, and evolution. Yet only a tiny subset of those systems might ever stumble onto the particular route that leads from chemistry to technology recognizable to us. The path that produces radio telescopes and starships might be just one narrow trail through a tremendously varied landscape. From one angle, that makes our situation feel even more precarious and special. We may be a rare offshoot of a process that usually stops at simpler forms. From another angle, it suggests that the universe is likely buzzing with activity in forms we have not yet learned to detect. Either way, it tells us that our current feeling of emptiness is more about our limitations than about the true state of the cosmos. We are still learning what to look for and what questions to ask when we point our instruments at other worlds. The next steps in this journey are already being planned. New space telescopes will sniff the atmospheres of distant planets for unexpected chemical mixtures. Missions to icy moons will taste their plumes in oceans. Sensors will map radiation belts, magnetic fields, and plasma structures with greater resolution. Each measurement will help us test whether life, in any form, is a freak accident or a common response to the universe's raw materials. The answer will not come all at once. It will emerge gradually, from patterns in data that may at first look like noise. As we gather those clues, a deeper question waits in the background. Suppose we do discover that life is widespread in bizarre and beautiful forms, yet almost none of it appears to build large-scale technology. What would that say about our own trajectory? Are we on a path that most living systems avoid for good reasons? Or are we part of a tiny minority that dares to restructure its environment on vast scales? To understand that, we will have to connect the chemistry of life not just to the possibility of minds, but to the grander patterns of history that decide which minds speak loudly, which remain quiet, and which never get the chance to try. When you try to connect the chemistry of life to the long story of the universe, you eventually arrive at a stark crossroads. Either we are early, we are typical, or we are essentially alone. Each option carries a different picture of the cosmos and a different message about what our future is likely to hold. The numbers we plug into our models, the way we interpret the silence of the sky, even the way we think about risk, all depend on which branch of that decision tree we believe we occupy. For decades, the Drake equation has served as a kind of mental map for this territory. It takes the process of making a technological civilization and breaks it into steps, from star formation to planets, to life, to intelligence, to detectable technology, and finally to longevity. It does not give a single hard answer. Instead, it forces us to write down our assumptions. Change one factor and your estimate of how many neighbors we might have can swing from almost none to millions. That sensitivity is not a bug. It is the equation quietly telling us how little we know. Still, some pieces have become clearer. The rate of star formation in the Milky Way is not a guess anymore. We can measure how many new stars light up each year. The fraction of stars with planets has been dragged out of the realm of speculation by thousands of exoplanet discoveries. Even the fraction of planets that sit in temperate zones where liquid water could exist looks generous rather than stingy. The early terms in the Drake chain want us to believe that habitable real estate is plentiful. Where the fog thickens is around the probabilities that life starts, that it becomes complex, that it develops intelligence, and that intelligent beings build technology we can detect. The hard steps model takes a different angle on this uncertainty. Instead of assigning each step a fixed probability, it asks how long these steps seem to take. On Earth, simple life appeared relatively quickly in geological terms. Complex cells, multicellular organisms, large animals, and technological intelligence took much longer. That pattern hints that some transitions may be genuinely difficult, the sort of steps that consume most of the available time budget on a planet. If the hardest steps are behind us, then by the time a species reaches our level of technology, it has already passed an unlikely sequence of hurdles. In that picture, we are the lucky winners of a series of cosmic lotteries. That would make the emergence of many Earth-like technological civilizations rare, but it would also mean that once such a civilization appears, it is not sitting right in front of another huge improbability. Its biggest dangers would come from self-inflicted wounds, rather than from some deep, almost impossible transition in biology or cognition that has yet to occur. If the hardest steps lie ahead of us, the story changes. Then a planet may produce many species with tool use, language, and fire, but almost none of them manage to stabilize their technology without destroying their base. In that case, a galaxy could be full of early-stage intelligent life that almost always burns out. The silence we observe would be the echo of countless failed attempts. When we ask whether we are early or typical in that universe, the answer might be that we are typical in our biology, but early in our confrontation with the most lethal challenges. We have just arrived at the dangerous gate. Looking at the larger, cosmic timeline adds another layer. Star formation in the universe peaked billions of years ago and has gradually declined. Many stars that formed long before the sun are still shining. Small red stars can live for trillions of years. Some researchers argue that the majority of potential for life and intelligence lies in the far future around such long-lived stars. If that is true, then we may be absurdly early compared with the main wave of civilizations that will someday fill the cosmos. Our story would be less like joining a crowded party and more like arriving hours before the doors open. Being early in that way carries both comfort and weight. It hints that the great filter might mostly lie behind us, at least in the sense of brutally improbable biochemical transitions. The path from chemistry to technological intelligence might be so difficult that only a handful of worlds manage it before the main epoch of gentle red stars truly gets going. At the same time, it suggests that what we do now could shape the context for all who come after. If early civilizations tend to expand, they could dominate huge regions of space, forcing later ones to exist only in the gaps. That idea is at the heart of what some call grabby alien models. In these scenarios, a small fraction of technological civilizations become expansionist in a very specific way. They send out frontiers that move at a constant fraction of the speed of light. Those frontiers do not drift aimlessly. They carve out growing spheres of influence that transform each region they reach, whether through colonization, engineering, or some other irreversible process. Over time, these expanding domains bump into each other and tile large chunks of the universe. Once a region has been claimed by one such sphere, it is no longer neutral territory for new civilizations to emerge and expand freely. If you live inside a universe shaped by grabby civilizations, your place in time contains information. You are unlikely to appear long after many such domains have already spread, because then your local region would probably already belong to someone else. You are more likely to arise just before or during the era when the first few expansion waves are starting to unfurl. That logic pushes us toward an uncomfortable thought. The very fact that we look out and see so much unclaimed space might mean we are early in the expansion era, not that there will never be one. From this perspective, the silence of the sky does not guarantee that nobody will ever shout. It may simply mean that the first shouts have not yet had time to cross the galaxy. When you combine that with our own recent arrival as a technological species, you get a strange possibility. We might be among the first potentially grabby civilizations, or at least among the early cohort. If we choose to expand aggressively later, our wave could be one of those that carve the cosmic map. If we choose not to, we might still have to deal with someone else's wave eventually reaching us. The core question then becomes, not only are we early or typical, but do we intend to be loud? A loud civilization in this sense is one that visibly reshapes its environment on large scales. It builds structures that intercept significant fractions of starlight. It sends out swarms of probes or settlers that leave unmistakable traces. It floods local space with engineered signals or waste heat. A quiet civilization, by contrast, might focus on internal development, minimizing its external footprint and perhaps even deliberately camouflaging its activities to avoid attention. At first glance, being loud has obvious advantages. It can spread risk across many worlds, reduce vulnerability to local disasters, and create vast reserves of resources. It can also satisfy deep drives toward exploration and creativity. From the standpoint of the universe, loud civilizations are the ones that dramatically change the look and dynamics of the cosmos. They are the authors of large-scale history. Yet the very traits that make loudness attractive might also make it dangerous. In a dark forest picture, being loud invites scrutiny and possibly aggression. In a thermodynamic picture, being loud often correlates with being wasteful and unstable. We face these choices already in miniature. Our energy use, our atmospheric changes, and our swarm of satellites are a tiny whisper by galactic standards, but they are loud compared with the background of our own solar neighborhood. Over the next few centuries, we may gain the ability to build giant orbital structures, mine asteroids extensively, and perhaps send self-replicating probes outward. Each technological milestone will bring a decision point. Do we prioritize rapid expansion or cautious consolidation? Do we broadcast intentional messages to other stars or focus on listening? Do we seek to become grabby or do we design our trajectory around long-term, quiet stability? These decisions are not abstract. They connect directly to how we handle our current crises. A civilization that cannot coordinate to avoid wrecking its own climate will struggle to manage the ethical and strategic complexities of expansion beyond its homeworld. A culture that treats future generations as disposable will likely treat other worlds and other forms of life the same way. If the great filter includes social and moral challenges, not just technical ones, then the way we govern ourselves in the coming centuries might be the real test of whether we are early and loud builders or early in brief accidents. There is also the possibility that we are simply alone, at least within the volume of space we can realistically reach or communicate with. Alone does not have to mean literally unique in the entire universe. It can mean functionally alone, in the sense that any other civilizations are so distant in space or time that interaction is essentially impossible. In that case, the silence of the sky is not a warning about predators or a hint about hidden empires. It is a straightforward reflection of the fact that nobody else is close enough to talk. The cosmic neighborhood might really be empty for us, with no neighbors coming. If that is true, then the stakes of our survival become enormous. The universe would still have countless stars, planets, and strange chemistries, but the particular experiment of self-aware, technologically capable life on this specific world would be one of very few in a vast volume. Extinction would not just be a local tragedy, it would be the abrupt ending of a story that might rarely get told. Under that assumption, even modest steps toward securing a long future for humanity and its descendants would have outsized importance. Our galaxy's worth of silence would be asking whether we are willing to take that responsibility seriously. Of course, we do not yet know which branch of the decision tree is true, early and surrounded by potential future empires. Typical in a cosmos where most civilizations burn out, functionally alone in a wide, indifferent space. The data are still sparse, yet we are not completely blind. Each new exoplanet we catalog, each atmospheric spectrum we analyze, each survey that looks for wasteful megastructures and finds none, helps us refine the probabilities. The absence of obvious Type 2 or Type 3 signatures suggests that loud, galaxy-sculpting civilizations are at best uncommon. Future telescopes may tell us whether simple life is widespread or whether Earth really is an outlier, even at that level. As those clues accumulate, the narratives we tell ourselves about our place in the universe will adjust. If we find many biosignatures but no clear technosignatures, we will lean toward a picture where life is common, but our technological path is rare and fragile. If we find almost no biosignatures at all, the conclusion might be that even simple life is a miracle, and that we are already guardians of something nearly unique. If we someday do see unmistakable signs of other technology, whether in an engineered atmosphere or a faint megastructure, then the entire framing of early versus alone will have to be rewritten. Until that happens, we live in a kind of suspended moment. We know enough to realize that the cosmos is vast and rich in potential habitats. We know enough to see that technological civilizations like ours are not obviously crowding the sky with their projects. We also know that our own situation is precarious, perched between the leaps we have already made and the larger leaps we might attempt. That combination of knowledge and ignorance is exactly what gives this era its strange, electric feeling. We are both tiny and significant, ignorant and yet in a position to make choices that may echo for millions of years. It is tempting to respond to that tension with either paralyzing fear or grandiose fantasies. There is another option. We can treat our ignorance as a reason to proceed carefully, but not as an excuse to stop asking big questions or making long-term plans. We can build institutions that think beyond election cycles and profit quarters. We can design technologies with safety and alignment in mind from the start, rather than trying to bolt ethics onto them afterward. We can decide that being early, if that is what we are, is not a prize to boast about, but a responsibility to meet. In the end, the Fermi Paradox is less about aliens than about us. It forces us to hold two truths in our minds at once. The first is that the universe does not obviously care whether we succeed. The second is that within our small sphere of influence, our choices matter enormously. Whether we eventually become a quiet, enduring civilization, a loud, expansive one, or a brief, bright flash that leaves only a thin chemical trace in the rocks, will depend on countless decisions made by ordinary people over many generations. That is a heavy thought, but also a strangely empowering one. The night sky will not answer our questions anytime soon. The stars will continue to shine with their indifferent light, whether or not anyone else is watching them from other shores. As we wait for better data, the most meaningful response we can give to the paradox of silence is to act as though our story truly matters, to safeguard the conditions that allow curiosity, compassion, and understanding to grow, to build a culture that could, if given the chance, survive long enough to eventually know for sure whether we are early, typical, or forever alone. The universe has left that part of the script unwritten. It is up to us to decide how to fill it.